So on the graph, I just thought of another example we'll do as well. Let's graph f of x equal to 5x squared over x squared plus 3x minus 10. And so I'm going to make this statement a couple times. When we're finding the y things, it is usually nice to have the unfactored form. When we're finding the x things, it is usually nice to have the factored form. So when I say the y things, I mean the y-intercept and the horizontal asymptotes, because the horizontal is y equals something. When I say the x things, I mean the x-intercept and the vertical asymptotes, because the vertical asymptote is x equals something. So let's find the y-intercept, if there is one. So set x equal to 0. You're going to get y equal to 5 times 0 squared over 0 plus 0 minus 10. 0 over not 0 is 0. Let's find the x-intercepts. So normally, so we could also factor this, right? Specifically, we could factor the bottom as x plus 5 times x minus 3. So let's see, x-intercepts, we're still setting just the top equal to 0. Again, I'll remind you guys, we could set the whole thing equal to 0, but when you set a fraction equal to 0, setting it all equal to 0 is equivalent to setting just the numerator equal to 0. So we're going to set 5x squared equal to 0. And then we're going to get x equal to 0. No big surprise, right? If the y-intercept is 0, one of the x-intercepts will also be 0. To find the vertical asymptotes, we set the denominator equal to 0. And you can see, right, we definitely prefer the factor denominator so that it's easier to figure out what the the vertical asymptotes actually are. So I'm going to set x plus 5 times x minus 3 equal to 0. We're going to get x equal to negative 5. And we're going to get x equal to positive 3. And I like to talk about the multiplicity of these vertical asymptotes. They're both odd multiplicity, which means they're going to do opposite things. So they're both going to do this kind of deal where you're up on one side and down on the other, or down on one side and up on the other. Right? Both of the asymptotes, one side will be going up to infinity, the other side will be going down to negative infinity. And then finally, the horizontal asymptote, let's write it over here. What's the degree on top? Oh, how did I get which terms, Alessandra? Oh, sure. So good question. Did I make, you know what? I might have made a mistake is when I, real good question because I made a mistake. It should be x minus 2. Sorry about that. I'd like to pretend I just accidentally wrote 3 instead of 2. Yeah, sorry. X plus 5 times x minus 2. That should be x equal to 2. Good call. Thanks for keeping me honest. So that's how that actually factors. Because 5 times negative 2 adds up to negative, or multiplies to negative 10 adds up to positive 3. Okay. Also, before I forget, do this. Okay. Any other questions? I needed that coffee, clearly. So, horizontal asymptote. The degree on top is 2. The degree on the bottom is also 2. So the horizontal asymptote is going to be y equal to the leading coefficient on the top, which is 5, divided by the leading coefficient on the bottom, which is 1. So y equals 5 is our horizontal asymptote. All right, throw it all on a graph. Let's see, so I've got 0, I need to go up 5. I also need some vertical asymptotes at negative 5 and positive 2. Okay, so there are all of our asymptotes. And again, I typically like to start at my y-intercept. In this particular case, we have to we need another point because we could go up, we could go down, right? I will re-mention again and again and again, we could go up because it's totally okay to cross a horizontal asymptote. I don't think we do here, but we could. So I'm going to pick a point like 1 and plug it into the function. So I plug in 1, f of 1 is equal to 5 times 1 over 6 times negative 1. I'm plugging it into the factor form because it's easier, I think, which is negative 6. So f of 1 is definitely negative, which means, right, we're down like here, like that. And on the other side, well, we know that these vertical asymptotes are odd multiplicity, meaning they do the opposite thing on the other side. So since this side is going down to negative infinity, this side has to be going up to positive infinity. You could also pick a point if you wanted to, right? You could check x equal to 3. If you plug in 3, you get 5 times 9, which is 45 on top, and 8 times 1, which is 8 over 1. So 49 over 8 is like 6-ish. So yeah, that seems reasonable that you can plug in 3, get like 6. Sure. Okay. I think there was something else I wanted to mention here before we did the other side of this graph. Guess not. Guess not. Okay. On the other side, I probably should have also mentioned that this x-intercept has a multiplicity of 2, because it came from setting x squared equal to 0, which has a degree of 2. So that means it's going to bounce. So we're down here, we're down here. You could also check a point over here, like checking x equal to -1. The top is still positive, the bottom is still negative. And then over on this side of this vertical asymptote, since this side is going down to negative infinity, this side has to be going up to infinity. And then as we go further out to the right or further out to the left, our function has to get closer and closer to the horizontal asymptote, which is y equal to 5. Questions about this one?
Professor, I had a quick question.
Go ahead.
I wanted to explain how you got.
Sorry, you're really breaking up.
Can you hear me now?
Perfect.
I just wanted to ask if you could further explain how you got the parabola on the bottom half
So
of
I wouldn't call it a parabola. Yes, it kind of has a parabolic shape for sure, but I will point out actual parabolas never have vertical asymptotes, right?
Yeah.
Like if I was going to draw y equal to negative x squared, for example, it would look like this. And I know sometimes we're a little bit lazy with our drawing, but I really want to emphasize, right? This isn't a vertical asymptote, right? It's not going ever vertical. It's still going down and to the right. And this is going down and to the left. But the way I got that shape was really just following kind of what I was forced to do, right? I picked a point over here. I picked x equal to 1. I plugged in 1. F of 1 is 5 over negative 6. And so once I got a negative number here, I had to keep going. Well, I guess I should say, when you have a vertical asymptote, the function either has to get negatively infinitely large or positively infinitely large when it gets very close to it. So since we were already negative and we had no x-intercepts to cross the x-axis with, we had to keep going super duper negative. On the other side here, what I did was I said, well, the x-intercept came from this factor with an even multiplicity. And when the multiplicity is even, it bounces off. That's how I know it's going that way. But we also could have checked another point. We could have plugged in, say, -1, and f of -1 would be 5 times -1 squared is 5. And the denominator is -1 plus I, which is 4 times negative 1 minus 2, which is negative 3. That would be negative 5/12, which is also a negative number. And then once I'm negative, I have to stay negative. So that's how I knew that I have that kind of shape there. It probably doesn't look exactly right. Like you graph this on Desmos, it would probably look a little bit different, but this is the general shape.
Okay, thank you so much.
You're welcome. Again, I really should emphasize, there are lots of things that we'll see like with trig functions also when we graph like secant and cosecant. There are pieces of it that look kind of parabolic, but they have vertical asymptotes. They're not actually parabolas, but they do kind of have a parabolic look. So we kind of think of them as like, oh yeah, that looks like a parabola. So remember, it's not. Okay, other questions about this? All right, let's do another one. Let's see. Yeah, I got tons of time. Where did my example go here? I'm done with you. Yes, I'm done with you. Let's look at this one. Y equal to 2x minus 6 over x plus 2 squared. And again, let's find all the usual things. So y-intercept, x equals 0, y is going to equal. So I want to encourage you guys to not you don't have to write everything out in super detail, right? Like if I'm going to find the y-intercept, I'm not going to do 0 minus 6 over 0 plus 2 squared. Right? I'm going to be like, oh, 0 minus 6 is negative 6, 0 plus 2 is 2, 2 squared is 4. So this is going to be negative 3/2. And then the x-intercept, or intercepts, we're setting the top equal to 0. And we're going to get x equal to 3. Vertical asymptote. Oh, also, I should point out that, right, this 2x minus 6, if you really want to, you could factor out a 2. Say it's 2 times x minus 3. But what I'm really trying to emphasize here is that this is to the first power, meaning it's an odd multiplicity, meaning it's going to cross at that x-intercept. Vertical asymptote, set the denominator equal to 0. So I set x plus 2 squared equal to 0. I'm going to get x equal to negative 2. Right, it's the thing that makes it equal to 0. Negative 2 plus 2 is 0. And that has a multiplicity of 2, meaning our vertical asymptote is either going to be up on both sides or down on both sides. All right, lastly, horizontal asymptote. Somebody please tell me, what's the degree on the top? 0, 1, or 2?
Would it be 1?
Right, the degree on top is totally 1. The degree on top is 1. And you're just looking for the highest power of x. What's the degree on the bottom going to be? 0, 1, or 2?
2.
Right, because now it's easy to make the mistake of saying it's 1 because you only see an x to the first. But if you multiply out the bottom, it's x plus 2 times x plus 2, which is x squared plus 4x plus 4, which has a degree of 2. So since the degree on top is less than the degree on the bottom, we know that our horizontal asymptote is y equal to 0. It's always the case when the degree on top is less than the degree on the bottom.
James, I have a quick question about multiplicity.
Sure.
What if we had something like x squared plus 2 to the power of 2?
So that one specifically wouldn't have any answers because x squared plus 2 never equals 0.
Okay.
But I know what your question. I see where you're going with that question, and I will try to incorporate that in my next example.
Okay, thank you.
It is a good question. Yeah. So let's look. So let's yeah, sure. Gosh. All right. So then we want to graph it. Let's see. I've got y equal to negative 3/2. halfway between -1 and -2. Got x equal to 3. I've got a vertical asymptote of -2. And a horizontal asymptote that I'm not going to draw at y equals 0. Right? So then I'm going to start here. And you have to go to the right and to the left. Let's go to the right first. That's just typical. I'm going to go to the right. I'm going to cross at my horizontal, at my x-intercept. And then since my horizontal asymptote is y equal to 0, we have to turn around and get closer and closer to our horizontal asymptote. Here's another example of crossing the horizontal asymptote. If we go to the left, well, we were out of x-intercepts. So since I'm already below the x-axis, I can't cross to be above it. I have to just stay below. And then since my vertical asymptote had a multiplicity that was even, this side going down to -infinity, so is this side. And then as we go further to the left, we get closer and closer to our horizontal asymptote. And that's our graph. Okay. Time is it? Yeah, I got enough time. One more example and then another example. Let's see what I do with that one. Okay. Let's do something. This one's gonna be kind of wild. I'm gonna make something up. Let's do. Do I want to? No, I don't do it. Okay, y equal to, what have I got here? Sure. X squared minus 4 times x squared plus 1 over x squared minus 1 squared. So it's kind of bonkers looking, no doubt. But let's just attack it like we normally. Let's find the things and we'll deal with what we have to deal with. So let's find the y. And set x equal to 0. If x is 0, then I'm going to get y equal to 0 minus 4, 0 plus 1, over 0 minus 1 squared. Minus 4 times 1 is -4, divided by positive 1 is going to be -4. Okay, let's find the x-intercepts. Find the x-intercept, you just set the top equal to 0. So I set x squared minus 4 times x squared plus 1 equals to 0. So I want to be very, very clear. X squared plus 1 can never equal 0. X squared is always greater than or equal to 0. X squared plus 1 is always greater than or equal to 1. So really, we're just setting this part equal to 0. So I set x squared minus 4 equal to 0. What are my solutions? Well,
Plus,
oh, go ahead.
I was going to say plus minus 2.
Exactly. The solutions are plus or minus 2. And what are the multiplicities of those solutions? Well, that's the harder part to answer if you haven't factored it, right? You might just look back here and we'll have the multiplicities too, but it's not. So if we go back and factor this further, x squared minus 4 actually factors as x minus 2 times x plus 2. So x equals positive 2, which came from this factor, x minus 2, has a multiplicity of 1. And x equal to negative 2, which came from this factor, also has a multiplicity of 1. It is important that you recognize which intercept came from which factor. Right? X minus 2 equal to 0 gives you x equal to positive 2. X plus 2 equal to 0 gives you x equal to minus 2. All right, vertical asymptotes. This is where things are going to be interesting. So we've got x squared minus 1 squared equal to 0. And I think this is what Jesus was asking about with his question about like if you have something square multiplicity. So what are the solutions here? X equal to what and x equal to what? Well, definitely 1 is a solution. I know I'm not showing my work. I'm trying to kind of skip over that to kind of. We get 1, and we also get -1. So the question here is, what's their multiplicity? Well, to see that, I feel like you really have to actually write it out. So the problem is, this way, it's really not exactly clear. So I'm going to do some factoring. So x squared minus 1 squared is, well, x squared minus 1 factors as x minus 1 times x plus 1. And then still squared. But then if you have a product squared, you can square each of the factors. This is really equal to x minus 1 squared times x plus 1 squared. So looking at it this way, we can see more easily that both of these vertical asymptotes have even multiplicities because of this right here. Hopefully that's addressing the question that was asked. Finally,
Yeah, that's more clear. Thank you.
Finally, for the horizontal asymptote, okay. I would say show me on your fingers, but I can't see your fingers. So everybody type in the chat, what's the degree of the top part of this rational function? Type a number. Yeah, that's right. Definitely 4. How about the bottom part? Right, also 4. So since the degrees are the same, the horizontal asymptote is the quotient of the leading coefficients. So we're not going to actually multiply that, but we can see that if we multiply it out, the first term here would be 1x to the 4th, and the leading term here would be 1x to the 4th. So the horizontal asymptote would be y equal to 1 over 1, which is 1. Great, we have all the information. Let's graph it. Okay. So let's see, I had the vertical asymptote at 1 and -1. I had the horizontal asymptote at 1. I think this function is probably symmetric, right? I think it's an even function. Yeah, it's definitely even, right? So if you replace x with -x, all of the x squared would still just be the same x squared. So it's definitely gonna have even symmetry. Let's see, we had a y-intercept of -4 and x-intercept of plus or minus 2. Okay. Since I'm down here, if I move to the right, the first feature I encounter as a vertical asymptote means we're going to have to go that way, right? There's no other choice. We can't cross the x-axis. Done. And then on the other side, the vertical asymptotes have even multiplicity, so we also have to be down this way. I would also mention that although you certainly could be above and come down and cross the horizontal asymptote and hit there and then bounce off, well, one, we know the x-intercept isn't a bounce, it's actually a cross. And two, if you don't have a reason to do a certain thing, usually the path of least resistance is the more likely one. So right, don't be crossing horizontal asymptotes unnecessarily. And then we can go like this, and cross, like that. On the other side, we can either do the same work. We can say, oh yeah, it's got to go down this way. This had even multiplicity, so it's got to be like this. I come up here and cross like that. Or it could have just been like, hey, I know this is an even function, so it's going to have symmetry across the y-axis, so it should look the same on the left as it does on the right. Questions about this graph? Okay, let's do one more, and then we'll start talking about some slant asymptotes, or obliques if you prefer. Let's see, so there's one I've got here. I'm going to modify this a little bit. So f of x equal to, sure, yeah, x plus 1 times x minus 2 times x minus 6 over, sure, I'm crazy, x minus 4 times x squared minus 1. And so for all of our examples so far, we've just jumped right in, right? We've said y-intercept, x-intercept, vertical asymptote, all. But I should have every time been factoring everything to make sure that nothing canceled. Now, nothing did cancel in this, so it wasn't a big deal. But here's something cancels. So if we factor the denominator here, we get x plus 1 times x minus 2 times x minus 6 over x minus 4 times x or minus 1 factors as x plus 1 times x minus 1. Now I want to stress, for this function, positive 4 and negative 1 and positive 1 all are not in the domain. Right? X can't be 4 because we're not allowed to divide by 0. X can't be negative 1 because we're not allowed to divide by 0. X can't be 1 because we're not allowed to divide by 0. The 4 and the 1 are kind of typical, but the negative one's a little different because the negative one, if you plug in negative 1 for x, you get 0 on top and you get 0 on the bottom. 0 divided by 0 is still undefined, but I want to make sure everyone's really okay with knowing that, like, that even if these cancel out, which they do, negative 1 is still not in the domain. So what we usually do when we factor and cancel something is we say, okay, our function is now this nice simpler version, x minus 2 times x minus 6 over x minus 4 times x minus 1. But we also have to remember that just because we cancel that out doesn't mean that we can just plop negative 1 in all of a sudden. We still have to disallow negative 1. So that's always the case when you factor in. Canceling a factor is the thing that would have made the denominator and the numerator 0. That value of x still is excluded. Okay. And what that means graphically is what we're going to have there, instead of having a vertical asymptote like we were going to have at 4 and 1, we're going to have a hole at negative 1. And I'll talk about y in a second. So let's graph it. So let's find the y-intercept. So y-intercept is, let's see, plug in 0 for x. Maybe I'll simplify. Negative 2 times negative 6 is 12. Negative 4 times negative 1 is 4. So we get 3. The y-intercept is 3. X-intercepts. Let's see, if I set the top equal to 0, x minus 2 times x minus 6 equals 0. I get x equal to 2 and x equal to 6. Both have odd multiplicity of 1. Great, so they both went across. Vertical asymptotes. I set the denominator equal to 0. I get x minus 4 times x minus 1 equal to 0. So I get x equal to 4, x equal to 1, both with a multiplicity of 1, meaning we're going to have the opposite things happening, right? 1 up, 1 down. And then finally, for the horizontal asymptote, if we were to multiply this out, we would have an x squared on top, we'd have an x squared on bottom. The degrees would be the same. The leading coefficients would be 1 and 1, so we would get y equal to 1. I think I can put this on here. Okay, so here's what this is going to look like. Let's see. 1, 2, 3, 4, 5, 6, 7. I might do some measurements with this in just a second, just to kind of think of something. So let's see. Yeah. Graph the things. Okay, y-intercept 3, x-intercepts 2 and 6. 2, 4, 6. Vertical asymptotes 4 and 1. 2, 4. Horizontal asymptote, y equal to 1. Okay. Again, I'm always going to start at my y-intercept. My y-intercept is above the x-axis. It can't cross before I get to this vertical asymptote, so we have to go up this way. Vertical asymptote is odd multiplicity, meaning if I'm up on the left, I'm down on the right. You can also test the point. It's hard to test the point though. Like you can test 1.5, I guess. That's 1.5. It's a negative times a negative times a negative times a positive. So the overall thing is negative. We cross, we go through the horizontal asymptote because we have to, and there's no crossing again to go back down, and then up to infinity. And then finally, this vertical asymptote also has odd multiplicity. So we're down here again, hit an x-intercept, we cross, and then we level out with our horizontal asymptote. To the left, all we have is just the horizontal asymptote. With one thing we have to know is that this function is not defined at x equals -1. So at -1, there's actually a hole. And there's a hole if you did plug in -1 to this function, where you cancel out the x plus 1, you would get, let's see, so f of -1 is something like -1 minus 2, so -3 times -7 over 1 minus 4 is -3. Wow, my brain. Sorry, -1 minus 4 is -5, and -1 minus 1 is -2. That's looking like 21 over 10, which is just a little bigger than 2. This is going to be -1 comma 21 over 10. We have a hole there. So why a hole? Well, because on either side of it, the function is really, really close to that value. Let me actually show you this. So -21 over 10 is -2.1, sorry, positive 2.1. Well, let me show you on decimals just because I think it's worth kind of seeing this, because not everyone is always super duper comfortable with what a hole is about. Let me share my screen. Sorry, let me graph this thing. Apparently I need to update something here. So let's see. So if we graph this, we are graphing the original function, y equal to x, right, x plus 1, say in parentheses, times x minus 2, times x minus 6, divided by x minus 4, x squared minus 1. Let's take a zoom out a little bit, but you guys can see, right, it does look a lot like our graph. And if you want, we can even add in the asymptotes just so you can see them, right? We can add in x equal to 1, and that. We can add in x equal to 4. We can add in y equal to 1. You can see them. Now, I know that they look like they're like crossing over each other because we're so far zoomed out. If you zoom in, right, they're never actually, right, it's just getting closer and closer and closer and closer and closer, but they never actually, right, touch each other. Except for, right, our function does cross the horizontal slope right there at apparently 2 2/3, which is 8/3. The point I was trying to make is there is a hole at x equals -1. So right over here, can I get there? Sometimes it's hard to see where it's actually there, right? -1 undefined. So why is it undefined there? Well, again, because it's 0 or 0. But you'll notice, right, that you can't even really see the hole because because of the fineness of the graph. But let's see. Right. So if you look at that point there, it does show as a hole if you actually click on it, which is kind of neat. But if you pick values really, really close to -1, that's all I want to do. There we go. Cool. So right, for this graph here, I can pick some values very, very close to -1. Let me just delete this. Like -0.9 or -0.99 or -0.99 or -0.99, right? So you can see as your x values get very, 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 very close to -1, the y values are getting very, 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 very close to 2.1. And the same is true on the other side, right? You do like -1.1 or -1.01 or -1.00, whoops, 0, right? Like a lot of ones, right? You're very, very, very close to 2.1. So that's why we graph this. I mean, that's what we graph it. It's supposed to be graphed, right? So we graph it with a hole. Sorry, there's something in the chat I'm not seeing. Yeah, exactly. This is, you would show that exactly how I've done here. by saying that at the point -1 comma 21 over 10 or -1 comma 2.1, you have an open circle there. That shows that there's a hole. And the function isn't defined there, but everywhere around it, the y values are very, very close to 2.1 when the x values are very, very close to -1. This is actually a pretty important concept. This comes up a lot in calculus when we start talking about limits, but that's kind of the idea there, is that if you have a factor that cancels, the value of x that would have made it 0, in this case -1, you're going to have a hole at that point on the graph, which we do indicate with drawing an open circle. All right. So let's continue on. Let's start finally talking about some slant asymptotes. Cool. So I'll mention, you might have noticed, you might not have noticed, so far all of our rational function examples, the degree of the numerator has always been less than or equal to the degree of the denominator, right? That's always been true. Well, no longer. We're going to have some examples of degree on top is greater. So class P, rational functions with slant asymptotes. So a rational function has a slant asymptote. Which I will usually call them slant asymptotes, but you might hear other professors or people or books say the word oblique. When the degree of the numerator, or the top, as I'm going to write, is exactly 1 larger than the degree of the denominator. So that's it. I mean, that's it. Well, that's not it. That's not how to find them. So, yeah. So a slant asymptote, we get them when this is the case. When you're going to have this exactly 1 larger, and they're going to look like a y, right? So they're going to have the form y equals mx plus b. So we're going to be drawing a slanted asymptote, so like dashed lines, but it's going to be not like vertical or horizontal, it's going to be slanted. So how do we find the slant asymptote? Well, this is going to require polynomial division. We'll definitely do plenty of examples of it. So let's look at this first example. We're not going to graph this one, we're just going to talk about how you find the slant asymptote for it. So let's say that our function f of x was equal to x squared plus x cubed plus 4x squared minus 2x plus 5. And the denominator was divided by x squared plus x minus 3. I should also point out, before I get carried away here, that a function cannot, well, a rational function cannot have a slant asymptote and a horizontal asymptote. If the degree on top is 1 larger, it doesn't have a horizontal, it just has a slant. And in general, if the degree on top is bigger, it doesn't have a horizontal. So, how do we do this? So I'm going to do the division, so I've got this divided by that. So I'm going to say, okay, I've got x cubed plus 4x squared minus 2x plus 5 divided by x squared plus x minus 3. So then the way we ask these questions is, so you're always looking at the highest power term in the divisor. So this is the thing on the bottom, that's the divisor that you're dividing by. This thing here is called the dividend, the thing that's getting divided into. And you ask, what do you multiply by x squared to get x cubed? The answer is x. X times x squared is x cubed. We have to multiply x by all of this. So x times x squared is x cubed, and then x times x is x squared. And then x times -3 is minus 3x. And then just like with division, After you do this part, then you subtract. So subtract x cubed minus x cubed is 0. 0x cubed, if you like. 4x squared minus x squared is 3x squared. And negative 2x minus is plus, so negative 2x plus 3x is plus x. Bring that in the next term. Some people do this thing where they like just change all the signs and add. That's also fine. It's just not the way I always do it. So then we repeat the process. This term doesn't really need to be here, but there's none of it. So then we ask the question, what do you multiply by x squared to get 3x squared? And the answer is, of course, what number? It's 3. Now, here's the thing I want to say. As soon as you get that last part up there, that constant term up there, you can stop. Our slant asymptote would be y equal to x plus 3. Now, why is that true? Well, if we did continue, we don't need to continue, but if we did continue, I'll do the, so everything I'm writing in red is work you do not have to do. 3 times x squared is 3x squared. 3 times x is 3x. 3 times negative 3 is negative 9. Subtract. 3x squared minus 3 is 0. X minus 3x is negative 2x. 5 minus 1 is 14. So here's the idea. Again, you can and you should stop at this point when you get to that. But the idea is when you take your function and divide it, when you do this division, you can actually rewrite your function if you want. You can rewrite it as the quotient, x plus 3, plus the remainder, divided by the divisor. And here's the idea. As x gets very, very large, or very, very negative large. So, you know, like when we talk about a horizontal asymptote, we're talking about what's happening to the function as x is getting really, really large. And when it's a horizontal asymptote, like in the previous example, no, I don't have a previous example. Like when a horizontal asymptote was y equal to 5, right? We were just saying as x gets very, very large, the function gets closer and closer to the horizontal line 5. Well, the same kind of thing is true here. Is now what we're going to be saying is as x gets very, very large, well, as x gets very, very large, this part here is going to get very small because it's a fraction where the degree on top is less than the degree on the bottom. So when x is like 1,000, the bottom is going to be like 1,000,000. The top is going to be like 2,000. So the fraction is going to get very, 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 very small as x gets large. Which means when we get really big or really negatively big, this is kind of all that matters. The function is going to get really, really close to x plus 3 plus a tiny little bit. So that's going to mean that y equals x plus 3 is the slant asymptote. Yeah. Where'd you go, example? Sorry. Okay. Yeah. So I do think I want to leave you guys. Oh, the red fraction we have in the rewritten version, the green fraction we have at the top. Yes. Yes. So this here, not that you ever need to do this, and this here, those are equal. But the point is that doing the polynomial division gives us this part, which is what we actually care about, the quotient. That's your slant asymptote. Unfortunately, I don't think we're going to get to examples of drawing the graph of the slant asymptote today. We'll do that tomorrow. Well, let me do a couple more examples of how to determine the asymptote. That is important. So definitely, you will need to be able to do polynomial division. It definitely comes up. Well, let's look at a few more examples. So how about f of x equal to x squared over 1 plus 3x minus 4x squared. This function have a slant or horizontal? Looks like it has a horizontal because the degree on top and the degree on the bottom are the same. So this has a horizontal asymptote. of y equal to, let's see, the leading coefficient on the top is 1. The leading coefficient on the bottom is -4. Okay, because the highest power is x to the second, and its coefficient is -4. So here the horizontal asymptote would be 1 over -4. Or I would probably write it as -1. How about this one? So kind of just kind of going back. So how about g of x equal to, what have I got here? X minus 1 over x squared minus 4. Well, here the degree on top is less, so the horizontal asymptote is y equal to 0. But what about maybe f of x equal to x squared over x minus 1? Well, now we're in a case where the degree on top is exactly 1 larger. And so the slant asymptote we find with polynomial division. So x minus 1 into x squared. Typically, when we're doing this division, I like to write out all the terms that aren't there. So this is x squared plus 0x plus 0. X times what gives me x squared? X times x is x squared. But then x multiplies all of this, so x times x is x squared, x times -1 is minus x. Subtract. Boom, 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 0. 0 minus minus is plus, so 0 plus x is x. No, that's not the case. So if our numerator has a lower exponent than our denominator, our horizontal asymptote is y equals 0. In fact, someone showed me a trick for this one time that I thought was kind of cool. The student actually was like, oh, you know what, so if the degree on top is less, you can also say, well, look, this is equal to 0x squared plus x minus 1 over 1x squared minus 4. Now the degrees are the same, and the quotient is 0 over 1, which is 0. Plug in the top part to the one that divides. I'm not sure what you're saying exactly there, Alessandra. What I'm doing here is I'm just saying I have x squared divided by x minus 1. And then I'm asking myself, what do I multiply by x to get x squared? And the answer is x. So then I do x times x is x squared, x times minus 1 is minus x. And then we subtract. X squared minus x squared is 0. 0x minus minus x is x. Bring down the 0. And then repeat. When you multiply by x to get x, and this is a dumb question, but when you multiply by x to get x, you multiply by 1. And we stop. But you don't have to do anything else. Your slant asymptote is the line y equal to x plus 1. If I was graphing this one, so yeah, I'm going to take just a minute to graph this one, just so you guys can see an example. It'll only take a second. This one's super easy. This function has a y-intercept of 0, an x-intercept also of 0, a vertical asymptote of 1, and the slant asymptote of y equal to x plus 1. So y equal to x plus 1 would have a y-intercept of 1, and x-intercept of -1. I'm not drawing the actual line, I'm drawing the dashed line like that. So then if I was going to graph it, well, starting here, if I pick a number slightly bigger than 0, like 1/2, 1/2 squared is 1/4, 1/2 minus 1 is -1/2, so I plug in 1/2 into the negative number, so it goes down to the right. This asymptote is an odd multiplicity asymptote, so I'm going to be up on the other side. And then I go down, but I don't have a horizontal asymptote. I essentially have to turn around and get closer and closer to my slant asymptote. You are not responsible for finding this point here where it turns around. Same thing to the left. This x-intercept is a bounce, so we bounce off, and then we have to get closer and closer to the slant asymptote. Okay, that's all I have. Sorry for taking